Hi, today we're going to learn about centripetal force. So let's get started with this. Okay, so if you remember, if a force is acting in the direction that an object is moving, so the object is moving this way, I apply a force to it, its kinetic energy is going to increase. Similarly, if we have an object that is traveling in the same direction, but this time the force is going in the opposite direction to its motion, so it's opposing its motion, well, it's going to lose kinetic energy. But one thing we haven't looked at yet is what if the force is doing neither? What if the force instead is acting at a right angle to motion? There's no forward component, so it's not going to gain kinetic energy. There's no opposing backwards force component, so it's not going to lose. It's going to maintain its kinetic energy. However, it's going to start moving at a different angle. So its direction is going to change, but its speed is not. So it's going to keep its kinetic energy, but it's going to move in a different direction in a circular path. So we call this centripetal force. So even though centripetal force doesn't change the speed of an object, it does change the direction. Therefore, it is causing, like all force, it is causing an acceleration because it's changing the velocity vector's directional component, even though it's not changing its magnitude. Uh, and so this centripetal acceleration is something we're going to dive into right now. So it always, one thing to know is centripetal force always points towards the center of a circle. And if you want to know why, just think of it this way. So acceleration is delta v over t. So let's say here's v1, and then vi, here's vf, okay? And notice these magnitudes are the same. I didn't change how fast it's moving, but I did change which way it's moving. And if I do the tip-to-tail method of vector addition, there it is. It's pointing straight towards the middle. And I put it in the midpoint between the two. So I wouldn't get too caught up in all this, but the point is that if I have a centripetal force, then that acceleration vector is going to point, and the force vector are both going to point towards the center of a circular path. So here's the equation we're going to use. So this is the first equation to learn the new year, okay? And it is this one, the acceleration centripetal. So the centripetal acceleration is equal to the velocity squared over r. And since F equals ma, I can then talk about the centripetal force. So the centripetal force is just going to be equal to ma, whereas a is the centripetal acceleration, which is v squared over r. So centripetal force equals mass times v squared over r. That's something we're going to be working with quite a bit in this unit. Now, one thing I need to point out right away, though, is that centripetal force really isn't a new kind of force. It's not like I have tension, I have friction, and I have centripetal. It's a directional distinction. What I'm saying is a force is being applied that is causing an object not to speed up or slow down, but to go in a circular path. So any type of the known force we've talked about, friction, normal, tension, gravitational, any one of those forces can cause an object to travel in a circular path and can therefore be uh, a centripetal force at certain times. So think about like a car going around a bend in a road, right? So what happens is, imagine if it was icy, totally icy, no friction whatsoever. That car just go in a straight path. The force that's allowing it to go in a circular path at a constant speed would be the friction force. So that friction force is pushing the car towards the center of a circle and providing the centripetal force. So let's just try writing an expression then. Okay, so let's just say I have a car of mass m that's going around a bend in a road that has radius r. And I want to know what is the fastest that car could go without skidding. So once it skids, that means I've exceeded the static friction force. I know it's kind of weird, but when a wheel touches the ground, its movement relative to the ground is zero, all right? Because the car is moving so fast forward that when the wheels are going backwards at the same speed, the net speed relative to the pavement is zero. Yeah, did I really need to go into that? Still, it exceeds the static frictional force. So let's just try this here. So if the force of static friction is exceeded, the car is going to skid. So what we can do this, we can say the static frictional force is the centripetal force. And so I'm just going to solve this then to see what that V would be. Okay, so the first thing that happens, as always, it seems like, is the masses cancel out. And then I'm going to simply multiply by R and take the root. And so what I get is the maximum velocity that car can go around that bend is equal to RGU under the square root. Now, I don't know if you've had an opportunity to ride a fair like this. Having grown up in America, there was a very popular ride called the Gravitron. Basically, you get in this big round room like a salad spinner. I don't know if you've seen one of those. And it just starts spinning. When it does, you feel like oh, you just feel glued to the wall. Okay, it's a really cool illusion. You can't see outside, so you feel like someone just turned on sideways gravity, hence the term gravitron. But really, if we could look at it from the top down, what we see is I just have this rotating room that you're standing in, and there's a wall. Okay, and what's happening really is this. At any moment in time, so right now we just said you're going around a circle. But I'm just looking at this moment in time. At this moment in time, your velocity vector is pointing straight up the screen. Okay. But if you notice, the normal force of the wall is pushing towards the center of the circle and is providing the centripetal force. So in this case, the normal force between your back and the wall, that is what's providing the centripetal force. All right. So basically, it's pushing you into a circular path, and now a lot of times, you feel like you're being pushed against the wall, like these invisible hands are pushing you against the wall. But really, that's an illusion. Really, what you're feeling is is the action reaction force. So really, the normal force is pushing you inwards, and so you're feeling that reaction force of you pushing the wall backwards. And so you're misinterpreting that as I'm being pushed backwards. And really, it's the wall's pushing you forward and you're pushing the wall backwards. It's hard when you have these reference frame situations. But let's just say this, okay? What if something went wrong with the ride and the wall panel that was holding you and let go? So now there's no longer any force pushing you. There's no more normal force acting on you. Everything's the same, except at this exact moment, the wall stops putting a force on you. It just falls away. Well, what would happen is you would just move in a tangential path, because at that moment in time, that's the way you're moving. You are moving this way. And in the absence of some centripetal force to push you out of that path, you're just going to keep going the same speed in the same direction because you have inertia. All right, well, let's try this one here. So College Board likes this one, and it's actually a pretty simple one. Okay, so imagine I have a top down view. I have this surface that's frictionless. I have this mass connected to a string. The mass is traveling just like it was in the gravitron, except this time it's a tension force rather than a normal force. And to provide that tension force, what I've done is this string goes through a hole in this frictionless surface, and on I've placed an object of mass 2m. Okay, and the idea is uh, I want to write an expression for what is the velocity that this object has to have, the speed it has to have, such that it has enough centripetal force to hold this up. So the centripetal force caused between this force on this one will keep it going in a circular path. All right, so let's just see how we do that. So I say, well, the centripetal force is equal to this equation here, m equals Fc equals mv squared over r. And I'd say, well, it is the tension force that's providing that, right? So that tension force is equal to 2mg, because this gravitational force is being canceled by the normal force here, but this one is not. So the tension force, since this is not accelerating up or down, is going to be equal to 2mg. So I'm going to put that over here because that's what's providing the centripetal force. Is this the pull on the string is towards the center of the circle. So that's my centripetal force. So 2mg equals mv squared over r. So the m's, as often as the case, go away. Gives me 2g equals v squared over r. So v in this case is going to be the square root of 2gr. It's really not that hard. It's kind of fun because it's not necessarily, it's very far from intuitive, to be quite honest. Our bodies were never, we didn't evolve to go in circles like this. Uh, and that's it. We're done. See you later.